Okay, another uniform motion. This one's got another little wrinkle to it that we'll talk through, but the method stays exactly the same. Read through it, pick out the three numbers in the question mark, find the equation that works for what we don't care about, and then solve it. This one, as we read through it, a ball is thrown up at 12 meters per second. We're actually thrown at 12 meters per second up. So this one, I'm upping our vector game. So our V1 is a vector. It's 12 meters per second, and that's pointing up. Because of gravity, it accelerates at 9.8 meters per second squared down. From the grammar and the funny unit, that's acceleration, and its value is 9.8 meters per second squared down. The ball stops at its highest point. We've seen this a little bit when we talked about the car skidding to a stop. If it comes to a stop, that means the second velocity is 0. Oops, vector hats. And the question is, how high does it go? Or in math language, what's the displacement? Before I get to the equation, we got to deal with this up-down thing. We did it before when we did relative motion, when we considered things going in opposite directions, running up a down escalator, things like that. To deal with opposite directions when we have vectors, we have to give them opposite signs. I really don't care which one becomes positive and which one becomes negative, but in this case, between the 12 and the 9.8, since they're opposite directions, one of them's got to be negative. The most common way, some textbooks brainwash you to always make it this way, but probably the smartest and most common way is to make up positive. So our V1 is positive 12 meters per second. Ooh. And then our A would be negative 9.8 meters per second squared. By giving them opposite signs, we take care of the direction, and then we can just solve it like we would before. When we read through this, I don't care about t, so we'll go to that list of equations. The one that doesn't have a t is the one I sometimes call the difference of squares equation. And it looks like that. Now it's just a matter of plugging in and solving. Our V2 was 0, so we have 0 squared. Take away the V1. The V1 was positive 12, which we'll have to square. All of that over 2 times negative 9.8. If we expand that out, our D is equal to 0, take away 12 squared is 144. So that turns into negative 144. All over 2 times negative 9.8 is going to be negative 19.6. You can double check on a calculator or maybe do that in your head. 144 over 19.6, it's pretty close to 144 over 20, so 7 and a bit. Double check on your calculator. I got 7.35. At some point we'll talk about number of digits, but just go with 2 decimal places for now. Now to finish this one off, in a way we're done, but we can do a little bit better. Everything was given in kind of vector notation with square brackets, so we should end that way. So to finish that off, let's put it in vector notation. D with a hat is 7.35 meters. Because it's a positive number, and way at the beginning we made our up to be the positive value, I know that this has to be pointing upward. So the displacement of the ball is 7.35 meters up. Or technically the way it's worded, it said how high did the ball go? The ball went 735 up. So in a way it's the exact same as what we've done before. Read the question, find your 3 numbers and your 1 unknown, figure out what equation works, do the math. The wrinkle was this time when we have vectors, opposite directions have to have opposite